Hello students, I am Tanmay. I welcome you all in my channel Chemistry of Molecules. So today we are going to discuss about the preparation of pyrrole from 1,5-dicarbonyl compounds. So previously I made a you can say similar types of video preparation of furan or pyrrole from 1,4-dicarbonyl compounds. You may think the process is similar like that, and we will discuss this in details today. Okay, so this pyridine is a 6-member heterocyclic ring, and by the way, I have uploaded many videos about aromaticity. I suggest you please visit those videos for your better understanding. Okay, so let's start. As you can see that this is called 1,5-dicarbonyl compound. Okay, by the way, what we will cover in today's lecture? Today's lecture we will cover first the basic concept retrosynthesis and mechanism for this process, role of aromaticity because it's an aromatic molecule, and comparison of this preparation with 5-member heterocyclic compounds. Okay, so lots of things to be learned. So let's first come to this point. See, this is the 1,5-dicarbonyl compound. 1,5 means this is 1, 2, 3, 4, 5. In this way, this is called 1,5, not from here or here. Okay, there is a difference. Fine, and it undergo reaction with ammonia and ultimately results in pyridine. So this is pyridine. So, question, if we consider the retrosynthesis, let's consider this corresponding synthetic equivalent of pyridine is this. So, if we want to disconnect this molecule, means disconnection approach if I try, then we can think like that in this way disconnection could be done. This so the precursor could be this is delta plus, this is delta plus, and nitrogen delta minus. Why? Because you can see nitrogen is an electronegative atom, so it prefers to have a minus charge rather than plus charge. Consequently, nitrogen is negative and carbon is a relatively less electronegative atom. So, compared to that, it can hold plus charge properly. And corresponding synthetic equivalent of this disconnection approach is this one, 1,5-dicarbonyl compound, because this is delta plus and this is delta plus. Got it? Fine. Now, so this is the retrosynthesis for this pyrrole preparation. Now mechanism. So let's do this mechanism of this process. So first, what is expected since ammonia is there, carbon is there, acid-base reaction. So how this ammonia will attack here? What it will result? It will result in imine formation. So first, this NH2OH, I am just avoiding this first NH3 plus, then proton exchange, I am skipping this step. Second step, what is expected, that it will push, it will leave. So ultimate product is this is imine, this. So there is a two chance that under this ammonia condition, these may undergo imine formation first, or one thing can happen that this lone pair of nitrogen can attack this center, and ultimately using a similar way, what it will result? A ring formation. And why this ring formation will prefer? Because we know intramolecular reaction are always favorable over the intermolecular, okay, due to proper conformation of both thermodynamics as well as kinetics. So this reaction, so after first attack, then this hydrogen is shifted from nitrogen to oxygen. Fine. Second step, what will happen? These will undergo elimination. Now at this stage you must be careful that we know that nitrogen can undergo its valency expansion up to 4, but this nitrogen is not in the p orbital. So what can happen? So this is actually in sp2 orbital. Careful. So don't show this that it will push and it will leave. No, it will not happen because this nitrogen is not available. This pyridine lone pair is not involved in the aromaticity because it is in the sp2 hybridized orbital. Okay. So this is the thing. So what happened? It will attack. Next stage, this will leave. So what will be the final product? Final product is this nitrogen is here, this. Now there is a problem, or you can say there should be a tautomerization. So it could have a tautomer, like means this hydrogen will be shifted to this because C double bond N compared to this is relatively more stable. Okay, yes, fine. So question, this is still not aromatic. So how to make it aromatic? So further we need to abstract two hydrogen, one from this and one from this. So actually this is nothing but oxidation, or in special term you can say aromatization. what it will result? It will result in formation of this pyridine derivative. Okay, so this is. So where is the problem lies? Problem lies in this step, aromatization. What could be used for this reagent? For example, actually it is an oxidation, FeCl3 pyritic acid. Even you can use those DDQ type molecule to make it aromaticity. So I have already made videos related DDQ, so if you want, you may see. Okay, so this is, but this process has some serious problems. What are the problems? The problems are, for example, I am showing that reaction will happen this, but if you think that these are two methyl groups, if you think, then what is the problem? This is fine, but there is another, because reaction medium there is ammonia. So in presence of ammonia can act as a base, and if it acts as a base, then there is a chance that it can result in aldol condensation. Aldol condensation means, okay, better to show the original form. This, it will be easy. So aldol condensation between this. What? See, this is a methyl, means it is actually a CH3. So one proton could be analyzed in presence of base, enolate formation, and that can attack here. How? Why? Because see, this is 1, 2, 3, 4, 5, 6. So attack means 6-member ring formation. So what is the product expected? So this carbonyl here, this methylene, this CH2, OH, this. And actually aldol condensation and generally not stop at this stage, it undergo alpha beta unsaturated carbonyl compound, this. So this is alpha, sorry, sorry, I made mistake, not this is alpha and this is beta, elimination, okay. So undergo this, so ultimately it will result. So this is the serious drawback of this process, or you better to say side reaction. How this drawback could be eliminated? First of all, this drawback could be eliminated if, okay, this drawback could be eliminated since the aldol condensation need alpha hydrogen. Alpha hydrogen is essential for aldol condensation. So if the molecule do not contain any alpha hydrogen, so there will not be chance of aldol condensation. How? So instead of simple methyl, you can take phenyl. Is it possible then? Obviously possible. But there is an issue. Issue means, if you see this molecule, this pH, this. So you can say that, sir, it is true that this molecule, this methyl part do not have any alpha hydrogen, but the other part have alpha hydrogen. What do I mean? This position. They also have alpha hydrogen. So can they participate? Logically they can participate intermolecularly, but not intramolecular. Why? If you want to do formation aldol here, actually minus charge will be generated here, then this, so ring number formation 1, 2, 3, 4. 4-member ring formation is not feasible, and we know intermolecular reactions are little, if you compare intra versus inter, this is intra is always favored. So this will not happen. But under selective reaction condition, what do I mean selective reaction condition? Selective reaction condition means, if you take for example a very strong Lewis acid like zinc chloride and a dehydrating agent acetic anhydride, so what could happen? Under this condition cyclization possible. What is the product? Product is this, okay. So under this reaction condition, this cyclization is possible. Okay, but our target was what? Our target was to prepare pyridine, not this molecule, but that could be done. How? Okay, let's show me the mechanism of this process. First of all, this can coordinate to zinc chloride. Okay, so if it can coordinate to zinc chloride, what can happen? That if it coordinates to zinc chloride, then the acidity of this hydrogen is expected to enhance. Then what happens? Actually Zn2+. So then there is a high chance that this will convert it into corresponding enol. Okay, this is OH. This is, so this, even not only this zinc can help to follow enol formation. Another way, zinc can also coordinate to this oxygen to increase its electrophilicity or electron deficiency. So what can happen? The lone pair here can attack. Previously they can attack because oxygen is not that much strong nucleophile, first point. Enolization is relatively less, second point. Third point, the carbonyl, this is not that much electron deficient. First of all, because it's a ketone. Second of all, there is a phenyl which is plus R effect also. So what can happen? It can open. Ultimately, what it result? Aldol type product formation. You may consider that this and the hydrogen will be shifted from this oxygen to here because it became O minus. So this is OH. This is the pH. Similar way. So next step, since acetic anhydride is there, OH is not that much a good leaving group. So reaction with acetic anhydride will result in acetate formation, ester formation. Now this proton could be eliminated. This and it's seen it became a good leaving group. So ultimately it will result in this. Fine. So but still not aromatic. How to solve this problem? This could be addressed by, first of all, take an oxidant like ferric chloride perchloric acid, iron 3. Actually this is the oxidant. So what happens? It oxidizes this material to form corresponding aromatic counterpart. Okay, hydrogen. Now see, oxygen is plus 3 valent. It has a plus charge. Generally you will not believe that oxygen having a plus charge, is it stable? Actually it is not stable, but it's produced. Okay. Why this is? Because this is under resonance. That's why it could be prepared. Second, perchlorate anion. Perchlorate is a very stable non-nucleophilic anion. It will not attack. That is the reason perchlorate. Second. So what happens? This is produced. Now, as I told, this is a very reactive molecule. If you give ammonia to this molecule, it resulted in the diphenyl pyridine formation. So 2,6-diphenyl pyridine. This is. Now question, how this is happening? Okay, let me explain. So actually, since you can see that because this oxygen is in plus, okay, attached to 2 carbon. Actually I have shown one canonical form. It has other canonical form also. For example, double bond from this side. So what happens? Since it's a very electron deficient, it could have another canonical form. You may consider in this way that oxygen is neutral. This pH and pH. It has a plus charges in here. Here all the elements are octet filled, but here not. So what can happen in next stage? Ammonia is significantly high nucleophilic, so it can attack at this position. Okay. So or you can see, you can show attack in this position and it can open. Both are same. So what it result? This is oxygen, this is pH, and this is NH2. Actually what can happen? This nitrogen first after attacking it become plus charge, so it releases one proton. So in medium there is a proton. So you may consider that this could be abstracted, this first of all activated. Second, this nitrogen can push its lone pair to ring because this C, it's a amine ether type, not stable. So what it results? These 2 double bonds are here. So it results in, actually this bond is opened. So this is OH, pH, NH2. See, this is actually a enol. Which part is enol? This part. So it can undergo tautomerization because enol compared to enol, keto are stable except aromatic system like phenol. So keto. So this bond will go fine. There is only double bond. So this is pH, this is NH2. Now see, this is amine, there is carbonyl, and it can attack in an intermolecular fashion. Okay, so it can attack intermolecular fashion and ultimately result in, this is the NH. After this will release one proton, and this O minus will abstract that proton. So find this is pH. Okay. Now see, these can push and this OH can leave. So ultimately, water elimination. So what is the product? This is the nitrogen. This. Okay. This in this way. Sorry, I make mistakes somewhere. Where I make mistake? Fine. This is NH2. Fine. Okay. Then there should, it is not a single bond, it's a double bond. I made mistake. This. So that's why there was a problem. So now if it is double bond, there is something else. What do I mean? So this nitrogen is previously in imine, not NH2. NH. So OH, fine. So now see the question. This nitrogen can't, but there is a proton and this could be abstracted and it can come back. And who can abstract in the reaction medium? There is ammonia molecule. Ammonia can abstract. So what it will result? It will result in, this is pH, nitrogen, this 2,6-diphenyl. Okay. So in this way this is formed. So actually previously we are making this aromatic system using this fake chloride perchloric acid, and this oxidation derivative is converted into this in this way. Okay. So this is the first mechanism. So now one problem we have faced during the first process, that we need a aromatization reagent. But if you think about the preparation of 5-member heterocyclic, then in that stage no aromaticity providing reagent was essential, because during the dehydration process or condensation process the aromatic ring was produced, and that is the reason or driving force for that reaction. Okay. Now question, how can we avoid this problem? Because this aromaticity gaining is the biggest challenge for this molecule preparation. So can we avoid this problem? Yes, we can avoid. How? First of all, you can see aromaticity part is, that is nothing but oxidation. Oxidation of what? Oxidation of this derivative into corresponding the pyridine derivative. So that is the main issue. It is the oxidation. So if we both way we can do. What? Actually this is oxidation, or you can say minus hydrogen, elimination of hydrogen. So this is both way could be done. One is oxidation, like ferric chloride, this thing, and hydrogen abstraction. In this, that is also oxidation. So this is hydrogen abstraction. So you can say DDQ, those type of molecule can be fine. Now question, what is the solution? Could it be modification possible? Yes, possible. How? First, one way. So option number 1. Let's take a derivative of ammonia. Means, what do I mean? Let's solve the problem first. After that, we will go to the reagent. So this hydrogen is not a good living group. Instead of that, let's put a good living group or better living group like hydroxyl. Okay. So what can happen? This could be abstracted during the reaction medium. This proton, it will come here, it will come here. OH will leave. So ultimately what will result? Will result this compound. Fine. Now question, what is the corresponding synthol for this? NOH. Means previously I was using NH2H. Since there was H, right now I am using NH2OH. This is actually hydroxylamine. Okay. So this reagent we can. And difference is that actually we are making a double bond, means 2-unit oxidation. If you check the oxidation number of ammonia, the oxidation number of ammonia in this molecule is -3. And what is this hydroxylamine? This is more negative, so this is -1. So already this molecule have taken oxidized version, oxidized ammonia. So we don't need to oxidize the molecule further. Okay, first. Second point, if you compare the basicity of ammonia versus hydroxylamine, ammonia is more basic, but hydroxylamine is more nucleophilic. Okay. Consequently, less chance of aldol, less probability of aldol condensation also. For the first step, First 1,5-dicarbonyl plus ammonia was reacting, then there is a chance of aldol condensation which results in some another unwanted product. So less chance for this. So this is one of the method. Got it? If you don't understand that part, please go to the first part and come back here. You can understand. Everything is same because one hydrogen was pending there. For that reason, we have taken OH. Fine. What is the second approach? We can add some leaving group. What do I mean? Means we can have, for example, some group attached here or here. Okay, let's attach one group here. So this is L. Okay, so you may think that there is an OH. Fine, it was leaving, and this is this. So now what to do? So we know that these will leave. Fine. So ultimately what will result? It will, under this condition, it will result this. But these hydrogen and these leaving group need to leave, because then actually in this way these hydrogen you can consider leaving. This is abstracting. So similarly it's leaving. So if it leaves means these attacks, it comes and it leaves. So what it will result? It will result the same pyridine moiety. Fine. It will result in this moiety. So question, what could be the leaving group? The corresponding synthon could be, or better to say, the equivalence molecule could be, this is the nitrogen, this, hydrogen, this pyridinium. You may argue, sir, preparation of pyridine, you are using pyridinium salt. Actually, it is not that you are exactly preparing pyridine. Substitute pyridine could be prepared. For that purpose, you may think this strategy. And there is a plus charge and there is a Br minus. Okay. So what could be the synthon of this? Okay, by the way, I haven't yet taught you how to prepare the 1,5-dicarbonyl compound. That could be done in two ways. One is ethyl acetate, means active methylene compound, and diiodomethane. You can react and ultimately get 1,5-dicarbonyl compound, or reaction of a alpha beta unsaturated carbonyl, which is a Michael acceptor and an active methylene group. I will very soon upload a video about the preparation of 1,5-dicarbonyl compound. Please read along with this video. That will be helpful for complete understanding. In order to reduce the time of this video, I am not explaining that. So what happened? How can you prepare? Actually, this could be prepared from, just accept right now that just accept this concept right now. After watching that video, it will be completely clear to you. Okay. So this is and this is the derivative. Br. Fine. Now question, what is this? The alpha beta unsaturated carbonyl could be prepared easily. Second is this, how to prepare? You can prepare this molecule by means nucleophile, like that. Okay. So this could be the strategy. And how to get this alpha haloketone? Halogenation or bromination of ketone under acidic condition gives selectively monobromo derivative. So that is the way. So I have uploaded this video previously. Please visit those videos. It will be helpful. For example, you can use Mannich reaction also to prepare a unsaturated carbonyl compound. Fine. Even aldol condensation also. Fine. So this. Okay. Now we have discussed the two ways and role of aromaticity. Fine. So this is the overall discussion of the preparation of this pyridine derivative from 1,5-dicarbonyl compound, which involves in two steps. First of all, nucleophilic addition, means seed-base formation. Second of all, aldol type reaction. Third step, dehydration. And fourth step, the important step, is oxidation or aromatization to get the 6-member aromatic compound. Fine. We have discussed the difficulties using ammonia. What are the derivative or substituent like hydroxylamine? One way that you can avoid the oxidation step using this derivative, or you can take this leaving group attached thing, because they undergo elimination to form the final pyridine compound in one step. So this is the overall discussion. I hope this video may be helpful for you. So thank you everyone for listening. If this video is helpful for you, please help me to grow my channel. First of all, subscribe my channel Chemistry the Mystery of Molecule, and please press the bell icon to get the notification of every single video I upload. Secondly, share this video among your friends so that many people will be benefited, and your share may be the help to your friends, because he or she may not know that I am uploading such type of videos which may be helpful for him or her. And most importantly or lastly, like the videos and make some good comments. It's a big achievement, and if you think some improvement, modification necessary, please don't hesitate to mention it, or all the comment and criticisms are highly welcome. So thank you again. Stay happy, stay blessed. See you in my